Hey, this is Adam Chlipala. At MIT, I teach a class on formal semantics and program proof using the Coq Proof Assistant. And this functional Perl is my chance to share with you an approach that we use in that class to get the interesting stuff more quickly. So there's actually quite a lot of coursework going on these days that builds on proof assistants to help students learn to reason about programs. Two of the best known materials are Programming Language Foundations and Concrete Semantics, which both start from students who don't have past experience with proof assistants. There are also other materials, including my own book, Certified Programming with Dependent Types, that are aimed at people who are maybe more interested in becoming experts on these tools and get into more advanced material. So let's think about the benefits of these different styles. On the left, we can start with students who have minimal background, just basic undergraduate stuff that we assume all of our graduate students come in with, and we can teach them how to use proof assistants, how to prove the correctness of programs. Whereas on the right, we get to more advanced topics that I at least believe are crucial for scaling to, say, correctness proof of real-world programs. How can we get some of the benefits of both sides here? In particular, if we think about what a typical software foundations course accomplishes, by the end of the first part on logical foundations, let's say students finally get how to think about induction, how to do their own induction proofs. And when they pass through the second part, programming language foundations, they can do manual proofs of such classic results as type safety and correctness of individual programs in simple imperative languages. Could we, within a single semester, ideally, push this further so that students can actually do automated proofs of shared memory concurrent programs that do interesting things with mutable memory? I will say yes. So the class that I offer tries to mix some of those advantages. We will only assume standard undergraduate background in programming and theory. We will still take every proof principle we introduce and justify it from first principles. But we will also work with full-featured object languages, that is, the languages that we study formally, that really let you write real-seeming programs. And we'll do a lot of proof automation to save students from having to spend their time on the less interesting parts of proofs. So how do we do that? How do we cut out the less fundamental parts of this kind of reasoning? So we all know, for instance, the beta reduction rule of operational semantics for lambda calculus, which depends on substituting a value for the body of a lambda binder. We worry if v were not a value but actually contained free variables of its own, then those could accidentally be captured during substitution if the same variables are bound inside the body E. And in some kinds of semantics, we actually do need to do substitutions that are not only on values. And then we get some pretty hairy requirements that have caused a lot of trouble for people doing mechanized proofs. Another related example, let's think about separation logic. One of the most famous ways of reasoning effectively about imperative programs. And here is the frame rule that was really at the heart of the original proposal for separation logic. Above the horizontal line, we see the premise, which says we've proved a precondition P and a postcondition Q for some command. And then we're allowed to conclude for free any larger specification where we take the same predicate R and we added onto both the precondition and the postcondition, describing the contents of some disjoint region of memory. This is a really nice, elegant way of thinking about why we can, for free, lift results into larger memories. Unfortunately, it comes along with this side condition. No variable occurring free in R is modified by C. So before we get to the fun part, we have to explain free variables of predicates and modified variables of commands. Is that essential? One last example before I get into the solution. Let's think about shared memory, multi-threaded programs. One thread is incrementing its local variable x and then writing the result into a shared pointer, and then thread 2 is doing a symmetrical thing. In model checking, we might explicitly explore the state space of this kind of program, considering every point where we have to choose which thread runs next. In one path, first thread runs doing its x increment, and then the second thread runs doing its write into the pointer. But in fact, those steps could have happened in the opposite order of that, and we wind up in the same state, independently of the order that we choose. And in fact, production scale model checkers need to notice and take advantage of commutativity properties like this one to do their jobs well. And to formalize the rule that lets us detect when two operations commute, you might, for instance, say a command that only touches local variables of its thread commutes with anything the other threads want to do. But now we need to be rigorous about global versus local variables, and we need to justify that reasoning principle. Okay, so what do these three examples have in common? Well, let me show you a demo. So I'm going to start with maybe a more conventional way of doing a calc embedding of a simple imperative language. And then I'll show you how we do it differently with the approach that I'm here to sell you, which is mixed embeddings. So by the way, this should make a decent amount of sense to a general functional programming audience. Hopefully only a few elements of this will be a little puzzling if you're not familiar with calc. For instance, this part shouldn't be too bad. Here's an algebraic data type defining syntax trees of expressions in our language. These are side effect free expressions, constants, variables, and two kinds of binary operators. And then here's a recursive function definition that, given a finite map giving values to the free variables and given an expression, computes the number the expression evaluates to. Then we have an algebraic data type of command syntax. This is where we have side effects. We're going to be able to read and write addresses in some mutable heap. So we have variable assignments, reading the value from a memory location into a variable, writing a value into a memory location, then sequencing and conditional. Then we can define our recursive interpreter for commands, which is basically threading through the values of our variables and our memory locations. That is a valuation and a heap, which are also the results of interpreting a command. I won't dwell on the details of how that all goes. I think most ICFP goers are used to writing recursive code like this that operates over syntax trees. And then finally, we can write a simple example program. I'm sequencing, reading from address 42 into variable x, and then writing back to that address the result of incrementing x by 1. I could also use an if in an example program here, because I put if in my language. But if I wanted to use a loop or recursion or pattern matching or concurrency, I would have to add any of those into my list of command forms. Concurrency is kind of hard, but the others we're actually going to avoid needing to add explicitly with the technique that I'm suggesting. Also, we're going to avoid the explicit variable management. Here we see I'm threading a valuation, telling what the variables are holding through all of this. The technique that I'm going to show you gets around both that and the need to enumerate standard control flow constructs that should be inherited by the language that you're studying, so you can focus your attention on, say, the interesting side effects that are the primary part that you want to prove theorems about. So let's actually do some surgery on this example. We will get rid of the whole notion of expressions. We'll actually inherit expressions from the meta language calc. Similarly, I will simplify our command language. This is actually going to look sort of like monadic programming. In Haskell, let's add a return construct that just takes a number as input and makes that the result of this command. We're actually going to change commands to generate results, not just cause side effects. And then I won't need this anymore. Let's take sequencing and turn it into a monad style bind operator. Looks like this. Takes two commands as inputs. First one's just a command. The second one's a function from the number that's the result of the previous command to a new command. And now all of our commands can return values. So reading a memory address no longer needs an associated variable. It just needs an address, and writing will take an address and a value to write there. And then that's it. I'll just ask calc to type check this for me. Yep, we're good. Okay. So next thing, let's just rewrite our interpreter. I'll remove the variable valuation because we've now pushed off variable tracking into the meta language calc. So I'll return a heap and a number when we interpret a command. The number is the result of the command. So for instance, when we return n, that gives us the original heap unchanged and n as the answer. Won't need assignment anymore. Won't need if anymore. I will want sequencing to remain under the guise of bind. It's going to look pretty similar, no more variable evaluation. And then I change it so that I evaluate the first command, then I take its answer, and the number part of that gets passed to the function C2. Otherwise, it's the same structure as we had before. And then reading gets simpler. We read an address, we write an address and a value. So reading leaves the heap unchanged, and then just returns the result of looking up address A, and then writing just writes the value we gave to the address, and then let's say whatever, returns 0 as its answer. All right. And before I rewrite my little example program, I'll just add a notation here. When I write this with a little left arrow and a semicolon, sort of like a do notation in Haskell, what that really means is bind C1 and then a little lambda abstraction around C2. And so I can rewrite this one much more naturally, I would argue, like so, and then like so, back to address 42, x plus 1. Okay, so this may remind some of you of a variable binding technique called higher order abstract syntax, well known in semantics and plain old programming, because we are representing binders with functions of the host language. A key objective of higher order abstract syntax is to avoid what are called exotic terms that let you basically introduce new programming patterns that aren't explicitly defined in your syntax trees. But when you want to get students going quickly, writing interesting programs and verifying them, it's a great advantage to be able to stealthily introduce new programming features without having to enumerate them in your syntax trees. So let me show you that in action here. I'm going to write a little function that that searches the first n addresses of memory for a 0. So n is the number, that upper bound on the part of memory to look at. And so this is a recursive function returning a command. What do? Look at n, and if it's 0, we're done. We return 0 because we didn't find a 0. Sorry for the multiple senses of 0 here. Otherwise, there's some address left to search. I'm just going to read from address n prime. And then if what I read is 0, then I'll return 1. We found a 0. Otherwise, continue the search, decrementing the function argument by 1. And there we have it. So this is cool because I've written a program that effectively uses if, recursion, and pattern matching. I didn't have to define a single one of these in my language of commands. They were all inherited from the meta language. And in fact, this kind of approach generalizes to let us mix arbitrary meta language control flow constructs with arbitrary object language side effects, not just mutable state. We can even do all kinds of concurrency. And this may seem familiar to you from, say, monadic I/O and Haskell for adding side effects. Yep, it's a very similar idea, but crucially, it supports induction on program syntax, which we need for all sorts of meta theorems. So we can add operational semantics, prove type safety, we can do Hoare logic, abstract interpretation, model checking. All that works great in this approach, and it's much more lightweight than more standard styles that you see in other sources. So that's pretty much all I have to tell you. The materials for this course, I think, are ready for other people to adopt today. You'll find the URL at the bottom of this slide, and please drop me a line if you're interested. Thank you.